So, hello, good morning, good evening, good night, everyone, depending where you are. We are starting this session trying to give a practical overview of how we used knowledge graph, and in particular Neo4j, for dealing with a tangible, high-risk industrial issue. So we are particularly interested in tackling explosions, like negative events that can happen in diverse industrial plants. So I will be introducing the project and the activities we have been conducting over the last few months, and I will be together with my colleagues Francesco, Simone, Antonio, Javier, Nakhal, and Elena, Stefana. Myself, I'm Riccardo, Patriarca, and I'll be the coordinator of this presentation and also the coordinator of the project we're going to talk to you about. So in the next slide, a bit of acknowledgement. As I said, this is not just a pure academic exercise. It is a funded industrial project with results to be shared with the national insurance company in Italy, which somehow trusted us well enough to fund this kind of new idea, at least for the field of industrial and safety management. In particular, the project is called RESET, and is about engineering resilience for a safe energy transition in different types of industrial plants. The funding body is INAIL, and that's the national insurance company in Italy for accident at work, basically. You see the QR code and a link to the website. Part of that is in Italian because that was a requirement. But anyway, through the end of the slides, you will also see links and emails in case you want to reach us out. So in the next slide, we just wanted to start with something that unluckily is quite infamous and quite historically relevant for what we're doing here. So in 1984, actually was the night of the 2nd of December, so it's about 40 years ago, there has been one of the most critical events in the history ever. So it's called the Bhopal accident for plant located in Bhopal, actually, Pradesh, India. And it has been considered one of the most critical events ever because we are talking here of about 4,000 people being killed by the explosion, plus about 500,000 people being exposed to toxic agents for the weeks after the event. So it has been something like 4,000 is the people dying that night, but another 4,000 died in the next 2 weeks because of the exposure to toxic agents. And, the story continued for year and year later with the consequences of the explosion on the health of people. So Bhopal 1984 is not unluckily the only serious or accident. We can even call them disaster. There's plenty of them in the history. And, in the next slide, we just plotted the number of events over time. You see that it seems that safety started to be quite critical after 1980s. You see the spike in 1990s and then a fairly stable trend afterwards, as we can see in the next slide. As we can see in the next slide. Why that? Why in the 90s there is this spike? Because there was an increased acknowledgement that we need to know more. We need to increase our knowledge of events. So we need somehow to report events. And that's the kickoff for our idea of using knowledge graph and Neo4j, because from that moment onwards, there was an interest in legislation, regulation, standards to ensure a standardized way of reporting about safety events in different industrial plants. That's what happens maybe you have ever heard about the Seveso Directive in 1982, Seveso Directive 1, 2, 2 bis, 3. In Europe especially, that's kind of mandatory. But there are other states where the regulation is still taken as a best practice, and even if it's not binding, it's still accepted to be a very good way to go for reporting safety events. But look at this graph. Over the last decade, the trend, is slightly decreasing. It's not really dramatically decreasing. It means that the number of accidents is somehow fairly stable. And that's another driver for our project, because we know that we have somehow reports, knowledge about events, and at the same time, we know that these events are not decreasing. So in the next slide, we're going to see what is this project about and what this pitch will be about. It's about indeed looking and developing tools for management in these high-risk plans to ensure that there is the right interventions at the right time for improving the level of safety and eventually reduce the number of accidents. We're going to use a model typical of system engineering that is called STAMP. My colleagues will describe that later, but we're going to pair it with a knowledge graph and with testing laboratory. So we have an experimental facility in our partner testing, as we speak, different type of substances and mixtures. So next slide, please. Objectives. We want to model this complexity, this socio-technical interaction, not just plans, but also people, organization looking into that. We want to pair it with experimental analysis, and we want to make a decision super system. We believe all these things can be reached with a conscious usage of knowledge graph and Neo4j. But without further ado, I'll give the floor to my colleague.
Now, as Riccardo said, that we have a problem to manage this complexity and also this to prevent this industrial accident. Is for that we have the background in which we know that in this novelty and in this modern area we have the industrial society landscaping which is changing so fast, and also the automation and globalization adding more complexity and other factors to need to be included in the analysis. And after that, we know that the safety management is more critical than the past, because we know more. We have more interaction and more actors involved in our industrial process. For that, we know we want to study this European directive in 2012. It's a CVSO directive that is. They give you the best practice and also guidelines to handling, storing, and production dangerous substance. Now, some background: we know that this industrial process they are called a socio-technical system, in which we have the social system, in which we have the organization, the agents, the human factors that they control and manage this process. On the other hand, we have the technical system that is our process, our artifacts, in which they real operate the process. Combining them, we have a joint cognitive system in which we have the interaction in these two words. That give us a complex system or complex socio-technical system. For us, the motivation of this research is how to approach or how to enhance this safety management system, this complex socio-technical system. How? Through STAMP principles, that is, give you a systemic view of the directive, and after that, analyze with data-driven model with knowledge graph supported by Neo4j to analyze this directive. Now, the methods, we divide this research in three phases. The first one is the data collection, how we can gather in this data through that document analysis and the interviews the main experts. After that, we build the STAMP model, the directive using the STAMP principles, identifying the agents and also describing the interaction and the mutual dependency of the agents, and to further translate this STAMP model into knowledge graph to analyze and to see how to extract this information of the directive. Now, the first part is the data documentation. We did a basic thematic analysis to study this directive, and after that, create a draft of the safety control structure to see who is the agents and how they interact between them in the prescribed process. And after that, interview some experts to improve the content of this safety control structure. And after, to the final validation, a focus group with all experts to create a robust model that extract and also capture all the processes in the directive. Now, so quick how the stamp principle or how the stamp model works. We have three characteristic or main factor that this is a systemic theoretic perspective that the stamp model study the entire system, the whole system, and we define a volume console, but after that we study all the interaction inside of this volume control volume, and after that they define, or the model define that the process interacts between the agents through control action and feedback loops that they give the activities or the task, and after give some information on how is the process is working. And after the last one, or maybe the more relevant, is the safety or the safety word is emerging, okay, or is arise between the interaction of the system. Now, some advantage or what is the benefit of this stamp model? We can handle the complex and the dynamicity of the system. Also, we address both technical and social factors in the system, and that way we incorporate the human world and also the machine world to see how they interact between them. And after we can capture some holistic view of some of the system interactions. Now, how to build this safety control structure? We need to define the system agents. That is the controller, that they give, the controller is the main actor that the control or the operates the process. The control process that it is the physical process in which they receive this task or this control action to also operate or to give the steady state of the process. And after we have the actuator that is maybe act in the control process, and after the sensor to receive the information or the feedback to send to the controller. Now we need to define the interaction between them. That is the control action. That is the downstream to upstream to downstream. That is the action, the task, that the activities that they need to provide to operate the system. And after we need the feedback. That is the information that they receive or the communication to give to the controllers to know or to communicate how is the process going, or how is the state or the feedback of the process. After that, we need to create a hierarchical safety control structure. That we know this process, there is define the hierarchy in the system, that we have in the bottom of the model, we have the controllers, and after that in the last of the model, we have the control process. And after, in this case, the process model and control algorithm, that is their set of rules or also condition that maintain the system safety. That is the knowledge of the controller or the control process, how the worded process works to also operate the system. Now, the problem statement. We can maybe ask some question which is the system element who send the higher number of feedbacks, or which is the shortest sequence of these elements to be informed to send a control action from the controller. And we have this an example, which we have the operation manager here, and we have the tank, and we see all the interaction between them, that how can the operation manager operate the tank in an industrial process. Now, for the first question, we know that these three here in the alarm, between the tank and the alarm, the level, flow rate, and temperature measure is the feedbacks that it inform the controller how the tank is operating in the process. And also, for example, which is the shortest sequence, we know that the tank and the worker, we see this path that is the tank, worker, and operation manager to give more information or communication, how is the process working, is this, that. Now, imagine that, okay, this is to Antonio, this is quite easy, but what is now if we including more information or maybe translating this directive that we see now, and Francesco, my colleague, they will say you.
Yes, good morning. So yeah, what Antonio was talking about is actually a problem, because the example that he showed you was quite simple. He applied the stamp principles, so he built this famous safety control structure with just a few agents that were interacting by means of some of them were controlling some agents and some of them were controlled by some other agent, and they exchange feedbacks and control action mutually. But in the real world, well, when we start modeling the real socio-technical system related to the management of critical safety critical industrial plant, as Riccardo was talking about, we end up with a very complicated model. That is the one that is shown in the slide here. You know, it's really big, so in the slide it doesn't fit in the slide, so it's difficult to read what's happening, what's written in there. But you know, at a glance, it's possible to notice that there are a lot of agents, a lot of blocks, and a lot of arrows connecting blocks. So a lot of feedbacks are going on, and a lot of control actions are going on. So to answer some similar question to the one that Antonio asked us before, so which is the agent that is sending the more feedback in the system, which is the shortest path to control an agent from by a controller, and this kind of stuff, it gets somehow complicated. And another aspect to be considered is that this control structure is just a picture of the system at a given time, and things could change, and even agents, some more agents could be involved in the management of safety in the process. Some control action may change as the directive and the laws changes in time. So we start thinking, next slide, please. Okay, so we start thinking for a way to formalize what we are reading in the safety control structure to then somehow systematize its analysis by using a knowledge graph. To do so, we start from the very beginning. So we started by formalizing an organizing principle for the graph by means of an ontology, an entity relationship model, in which we put all the concepts that were identified in the stamp model to give a sense to the data that we will eventually put in the graph. So here in this slide, it is presented the ontology that we developed, that is meant, of course, to analyze the safety control structure, a safety control structure, and it is made up of 8 classes. It has feedback and control action, that are the exchange of information by agents. Then agent could be controller or controlled process, as Antonio said before. And then this feedback or control action could be transferred by sensors and actuators, or even the controller could develop his control action through an algorithm, a control algorithm, and through the idea he has on the controlled process. So the block named the model here. Of course, all these entities connect between each other, and so we have type of relationships too. For example, we can see the red arrows, controlled process, that could be related, could have a sensor here, or a control action can act on, so the yellow arrow, on a controlled process. Next slide. Yeah, by means of this ontological model, we could be able to translate a safety control structure, so something that is adhering to the stamp principle, is modeling the world around us following stamp principles. So there are there are controlled process, there are controlled, and so on. and we can translate it into a knowledge graph because we have an organizing principle to give a sense of nodes and relationship inside the graph. But we found one last barrier, let's say, because we had to find a way to apply the organizing principle on something that is the safety control structure. So if the ontological model give us, the concepts, idea about the concept that were present in the safety control structure, we had to tag it, let's say, manually. But we found, a kind of pattern also in the connection depicted in the safety control structure. So in the next slide. Okay, perfect. So we developed an additional tool that permitted to apply the organizing principle not on the graph, but on the safety control structure. I'll give you an example, even if I have really few time. But if you notice the structure that we presented before, you could spot that each controlled process sends a feedback that is moving from the top border of the controlled process to the bottom border of a controller. So, and this kind of logics could be spotted for every type of connection. So following this pattern, following this logic, we developed an algorithm, a Python script that, starting from a picture of a safety control structure, you see Visio here because it is the software that we use to build this safety control structure. Starting from a picture, so an XML file, actually, it spot all this pattern, all these logics of connections, and it applies the organizing principle based on the connection that he found and create a table, a CSV file that is saying us, okay, here there is a block that is a controller and it is connected to a sensor or whatever. Once we have the CSV file, we actually import the CSV file into Neo4j, and we got, please next slide, an actual knowledge graph. That is, here is maybe it's not clear what it's representing, but we have applied the organizing principle to the graph. So we have here nodes that are labeled as controller, nodes that are labeled as controlled process, and all the interaction that we developed in the ontology.
So, good morning also from my side. As my colleagues highlighted before, there are huge benefits from the use of an ontology, from this conversion from the STAM model to the knowledge graph. So this ontology permits describing indicators for different agents, controllers, and managing the information in any socio-technical systems. And we also can identify paths between controllers and controlled process in order to identify interesting interesting paths from a safety point of view. But this ontology could also permit predicting any kind of missing links when we deal with changing data, new data within a knowledge graph. And in addition, we could also include additional organizing principles for the knowledge graph. Next slide, please. So by means of an ontology, we could perform a joint analysis, in the sense that we could employ a semantical approach, in the sense that we could explore the knowledge graph through stamp-related semantics, in the sense that we are interested not only in the structure of a graph, but we can use the taxonomy, the nomenclature typical of a stamp model for navigating, for understanding better, the knowledge graph. And the second point is the possibility to perform an analysis through the meaningful metrics that a knowledge graph could highlight in order to understand the topological properties of a typical knowledge graph. So we could perform a joint analysis in both, in the sense that both graph significance and graph structure. And we could merge, we could integrate the information provided from these different perspectives. So our project wants highlighting that we could perform an analysis that, starting from different kinds of data, for instance, regulations, industrial data, procedures, information, but also the information provided by different experts, we could merge them in a manner that, passing through the stamp model, employing the stamp principles, and converting it in a knowledge graph, we could obtain a tool, a solution, a user-friendly solution to support the decision makers in the management of critical socio-technical systems, but mainly for the management, for the safety management of industrial plants. So we want to highlight the possibility to integrate the strengths of the stamp principles into a knowledge graph, and the use of this knowledge graph in the support, in the risk assessment, and in the safety risk management. In this presentation, we focus on the case of the Seveso directive, on industrial plants interested in managing of hazardous substances, but we believe that this kind of integration could be applied in different domains relevant from the safety perspective. An interesting point of view is also provided by the fact that we could link data from multiple sources, and these multiple sources are quite different each other, and the possibility to leverage on different multiple sources can reveal new insights in the safety domain. So next slide, please. So we want to thank all the experts that provide very interesting insights in the project, and that were involved during the data collection and model validation steps, in particular Mrs. Silvia Ansaldi and Patrizia Agnello. So we want to thank you everyone that participate today, and we obviously are available for any issues, curiosities, or anything else. Thank you.